This is the first problem, and this is very simple question, and I think every students can attempt and solve this problem. Number one, this is what if 60% of a number x is 40, then what is the x percent of 60? So we can simply solve this as 60% of x is equal to 40. So we can write 60x by 100 is equal to 40, and also x percent of 60, this is equal to x into 60 divided by 100, which is equal to 60x by 100, and this is equal to 40. We can also solve this as if 60% of x is 40, means x into 60 by 100 is equal to 40. So we have x is equal to 40 by 60, and now this is given that what is x percent of 60. So x is here 4000 by 60. So x percent means this is of 60 means this will cancel out, and we have the result as 40. So we have two methods for this, and the solution will be 40. Now the problem number 2 is find the number of positive integer n less than or equal to 100 which are divisible by 3 but are not divisible by 2. This is also very simple problem. First of all, we have to find out the multiples of 3, but the last positions must not be 2, 4 or 6 and 0. So here if we use the greatest integral value of the division of 100 by 3, and also we subtract 100 by 6, so this will be equal to 33.3, and here minus this will be equal to 16.6 something, and this will be equal to 33 minus 16, and this will be equal to 17. So here 17 is the solution. Also we can find out the multiples of 3 as we know that if we have any number, then sum of the digits if divided by 2, it means that is sum of digits if divided by 3, then this will be the multiple of 3. So now we have the first value is 3, the second value is 9, the third value is 15, the fourth value is 'So we can count this like 3, 9, 15, 21, 27, 33. So now if we count 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 and 17. So total we can count the all the numbers are divisible by 3 but not by 2, so the same answer 17 we got here. So this is also very simple problem. Now we have the problem number 3. Here in this problem, the area of an integer sided rectangle is 20. What is the minimum possible value of its perimeter? So this is a very simple problem. We can solve this like if we use the concept that we have the area like xy. If we use the length and breadth by x and y, this is equal to 20, and also we have both x and y belongs to integer and positive, so the perimeter will be 2 times x plus y, and now we have the x and y as integer 4 and 5, both are co-prime. Here 4 and 5 are co-prime, and now we have the perimeter will be like 2 times 4 plus 5, and this will be equal to 2 into 9 is equal to 18. So this is the first solution we have. As the perimeter, the minimum value will be 18. Now we can also use the inequality AMGM. We know that x plus y is greater than or equal to twice of square root of xy, because this is the length, so x and y both are positive integers. So now we can use the area, that is root 20, and now we have 2 times x plus y is greater than or equal to 4 square root of 20, and we know that the square root of 20 will be like 2 root 5. So we can use the value of square root of 20. And this will be like 17 point something. So this is perimeter, and that must be greater than or equal to 17 point something, but we have to use positive integer for our answer solution. So for the value 17 point something greater than, so we have the first integer is 18, so we have to take the least integral value of 17.5, and that will be 18. So we have the solution for the minimum perimeter will be 18. Also the third method we have, this is the first method, this is second, and the third method is, we know that if we use the square, so in this case we know that if we use a square, means all the sides are equal, will give the required perimeter. So if we have the area is 20, so now if this is a square, then a is equal to a square root of 20. This will be like if we use the 4 side, so 4 times a is equal to 4 a square root of 20, and this is the same value like this. So in this case we can say that the minimum value of this perimeter will be 18. Also we can see here, if we use the rectangle of any length of sides, then the area will be same, but the perimeter will be vary, like the perimeter will increase always, and this is the only case of a square when the perimeter is minimum. So we have to use the area of a square and finding sides. So a is equal to a square root 20, so 4 times side is equal to perimeter, and this will be equal to 4 times root 20, and this will be like 17 point something, and we have to use integer, so 18 will be the least possible value of the perimeter. Now for the problem number 4, we have to calculate the number of isosceles integer sided triangles are there with perimeter 23. So suppose we have a triangle like this, and the lengths are A and C. Now here 2A plus C is equal to 23, and 2A is greater than C, so this will imply the value of A and C is 11, also 10, 3, same 9 and 5, 8 and 7, 7 and 9, and 6 and 11. So we have the total number of isosceles integer sided triangles are 1, 2, 3, 4, 5 and 6. So total 6 possibilities are here. Now we have the problem number 5 here, like how many 3 digits numbers ABC in base 10 are there with A not equal to 0. In this problem, first of all we have ABC is a 3-digit number, and also we have A, B and C are integers and positive integers. So in this case we have the limits for A is greater than or equal to 1 and less than or equal to 9, and also we have B must be greater than or equal to 0 and also C must be less than equal to 9. So we have the values as C is equal to A plus B. So the possible values for C when we have A and B are integers. So in this case we can use C when C is equal to 0. Then we have A and B will be 0 and 0. Then if we use C equal to 1, then we have the value of A as 1 and for B 0. Now if we use C2, then we have A 1 and B1, and also we have if we use A0 then A2 then B0, and if we are using C3, then we have the value like 1 2, the second is 2 1, and the third is 3 and 0. And if we use the value of C is 4, because we have to go up to 9 for C. So if we use C as 4, then we have here we are using C3, then we have the following pairs like 1 3, 2 2, then 3 1, and also 4 0. Now if we use C is equal to 5, then there are no any pair when we use 6, then also no any pair if we use 7, then also no any pair if we use 8, then also no any pair if we use 9, then we have the value as for AB, which we have the value 1 8, and the second value will be 9 and 0. So here the following pairs we have this and this. So now here we can write the sum of the total will be like 9 into 10 by 2, and this is 90 by 2 is equal to 45. So we can form the total 45 3-digit numbers in base 10 are there with A not equal to 0 and C is equal to A plus B. So the total number of possible 3-digit numbers are 45. Now we have the problem number 6. In this problem, the age of a person in years in 2025 is a perfect square. His age in years was also a perfect square in 2012. His age in years will be perfect cube m years after 2025. Determine the smallest value of m. So now if we use the year of birth is equal to, like if we use the year of birth is equal to y, then 2025 is equal to y plus a square, and we are using this equation a. Now 2012 is equal to y plus b square, and if we use this equation as b, now n cube is equal to a square plus m, and we are using this as equation number c. And now from a, b and c we have a square minus of b square, y will be cancelled out, and this is equal to 13 into 1, as we have a and b both belongs to integer positive, and now a is equal to 7 and b is equal to 6 are the possible values of a and b. Now this will imply n cube is equal to 49 plus m, and now this will be perfect. Just above 49 is m, so this is the number 64. After 49, 64 is the number which is perfect square. So if we take difference, then we have 64 minus 49 is equal to 15. So this is the required solution for the result. Now here we have the problem number 7. In this problem, this is given that the sum of two real numbers is a positive integer n, and the sum of their square is n plus 1012, and find the maximum possible value of n. Now we have here a plus b is equal to n, and a square plus b square is equal to n plus 1012. This is given that the sum of their squares, we are assuming the two real numbers is a and b, so the sum of squares of a and b is a square plus b square, and this is equal to n plus 1012. And now we have here a square minus a plus b square minus b is equal to 1012, and now a minus 1 by 2 whole square plus b minus 1 by 2 whole square is equal to 1012 plus half, and this is equal to 2025 by 2 is equal to 45 square by 2. And now if we assume a minus 1 by 2 as here we have to use a concept that a cos theta plus b sin theta is equal to c, and if we divide square root of a square plus b square, square root of a square plus b square, square root of a square plus b square, so this will be like a minus 1 by 2 is equal to 45 by square root of 2 cos theta, and here b minus 1 by 2 is equal to 45 by square root of 2 cos theta. Now we have to use this as n is equal to a plus b, as n is equal to a plus b, and this is equal to 45 by root 2 sin theta plus cos theta plus 1, and the maximum of a plus b is equal to 45 root 2 by root 2 plus 1, and this is equal to 46. So now we have the value of n is equal to 46. This is maximum integral value when a is equal to 23 and b is equal to 23. So total value of a plus b is equal to 46 we have. In this problem, a quadrilateral has 4 vertices A, B, C and D, and we want to color each vertex by one of the 4 colors, red, blue, green or yellow, so that every side of the quadrilateral and the diagonal AC have endpoints of different colors. In how many ways can we do this? Now, here first of all we have to form a rectangle like this. Here A, B, C and D, and every side and the one and only diagonal here AC must be of a different color. So we are using this as a green color. This must be different color. So now we have here that A is not equal to B, and also A is not equal to C, and also A is not equal to D. B is not equal to C, and C is not equal to D. So if we use the case A, when B not equal to D, then all the 4 vertices are of different color, and all the vertices are of different color for this case. Now if we use the total number of ways, that will be factorial 4, and this will be equal to 4 into 3 into 2 into 1, this is 24. Now for the case B, if we use B equals D, then in this case we have the following arrangements, like 4C1, then 3C2, then 2 factorial, and this is equal to 4 into 3 into 2, and this is 24. So basically this way is to choose the repeated color. For repeated color, this is for the choose of other 2 colors, and this is the ways to color A and C for A and C. So we have the total 24 here and 24 here, So total 48 ways we have. Total number of ways is 48 we have. Now we have the question number 9. In this problem, in question number 9, we have the four sides and diagonal of a quadrilateral are of lengths 10, 20, 28, 50 and 75, not necessarily in that order. Which amongst them is the only possible length of the diagonal? So now we have the following inequalities for this quadrilateral. If we form like this, and suppose this is the diagonal, this is E, this is A, this is B, this is C and this is D, then we have the following inequalities. First of all, D must be greater than C, and also D must be greater than A, and also the sum of A plus B must be greater than E, and the difference of A and B must be less than E, and also C plus D must be greater than E, and also D minus C must be less than E, and this all the cases are for the triangle, and if we are using A is less than B. So here in this case the quadrilateral will imply the value of D must be less than A plus B plus C by using all the inequalities above. Now we have the following cases here. The case A will be for E is equal to 75, the last case we are using, and in this case we have 2E is equal to A plus B plus C plus D, and now in this case 150 is less than 10 plus 20 plus 28 plus 50, and this is equal to 108. So this is false. Now for the second case, if we use case B, then we have E is equal to 50, and now this will imply the value of D is equal to 75, and this is less than A plus B plus C, and this is equal to 10 plus 20 plus 28, and this is equal to 58. So this is also false. Now if we use case C, then we have, if we are using E is equal to 10, we have the following result. For D is Like if you use E is equal to 10, then the existence of pairs like 20, 28, 50 and 75 will not be considered, because the both have different among the non-less 10 as the minimum of 75, and 20, 28, 50 will be 25, which is which is greater than 10. So in this case there doesn't exist two pairs for this. Now if we use case D, then in this case if we use E is equal to 20, in this case also does not exist two pairs amongst 10, 28, 50 and 75, because both pairs have different among the numbers less than 10. So in this case we have if we use 75 and 50, so this is 25, which is greater than 20. So in this case we have the values for E will be 28, D is equal to 75, C is equal to 50, A is equal to 20 and B is equal to 10. So total values of E, A, B, C, D and E we have here. So in this case we have the solution for the value of diagonal E is 28 here. This is the following solution. Now we have the problem number 10. The height and the base radius of a closed right circular cylinder are positive integers, and its total surface area is numerically equal to its volume if its volume is k pi, where k is a positive integer. What is the smallest possible value for k? Now for this first of all we have to form a cylinder like the height is h and the radius for the circular base is r. So we have the volume pi r square h, and this is equal to k pi, and here RH is equal to 2 into r plus h. So now we have RH minus 2r minus 2h plus 4 is equal to 4, and if we factorize, then h minus 2 into r minus 2 is equal to 4. Now we have the following cases, as we have like the first case is 1 into 4, the second case is 2 into 2, and the third case is 4 into 1. So now the value for r and h we have like the value 6 and 3. Also the second value is 4 and 4, and the third value is 3 and 6. So here RH belongs to these values, and now we have to find R square H. So this will be equal to 3 square into 6. This is equal to 54. So we have the value for K is equal to 54. This is the minimum value actually for K. Now we have to solve the problem number 11. In this problem, for this, if this is given that A by B is not equal to 3 by 4, and also the GCD for A and B is equal to 1 and B is less than equal to 15. If we consider A is equal to 3K plus X and B is equal to 4K plus Y, then we have K, X and Y all belongs to integer, and also 4K plus Y is less than equal to 15. So we have the value of M is equal to modulus of A by B minus 3 by 4, and this is equal to the value 4x minus 3y by 4b modulus. And in order to the minimum M, consider B is equal to 15, then Y is equal to minus 1, X is equal to minus 1 and K is equal to 4. We have modulus of 4x minus 3y is equal to 1, and this will imply A is equal to 11, and finally we have the value A plus B is equal to 26. So now the smallest possible value for 4x minus 3y is 1, and xy is minus 1 and minus 1, two values are here. So this is valid for the largest possible value of the denominator is dependent only on B, and the maximum value of B is 15. This is B maximum. So finally we have to use the number 26 is the largest possible sum. This is the value of A and B as a sum. So A plus B will be 26. Now we have the problem number 12. In this problem, this is to be considered 5-digit positive integers of the form ABCAB that are divisible by the 2-digit number AB, but not divisible by 13. What is the largest possible sum of the digits of such a number? So now if we multiply this number ABCAB by 13, and we have like the number 1001 is equal to 7 into 11 into 13. These are the prime factors of 1001, 7, 11 and 13, all the pairs like 7, 11, 11, 13 and 7, 13 all are the co-prime numbers and the pure prime numbers. So in this case we can write ABCAB as a digit is equal to 1001 into the digit the two-digit number AB plus 100C, and this is equal to 100C mod 13. Now we have the 100C not equal to 0 mod 13, and this is basically for all C belongs to natural numbers. And now here if we use AB and ABCAB as dividend and divisor, like AB divides ABCAB, then this will imply ABCAB equals 0 mod AB, and also this will imply 100C is equal to 0 mod AB, and the two-digit factors of 100C with the highest digit sum will be 75. This is the highest digit sum, and here C is equal to 9. The largest sum of digit is now we have to use like according to ABCAB, this is like the first is 75, so 75, the third is 9, so this is ABC and AB, so again this is 75, so 75975 is the number of 5 digits. Now we have the problem number 13. There are 3 sides of a quadrilateral. Area A is equal to 4 square root of 3 and B is equal to 9 and C is equal to square root of 3. The sides A and B enclose an angle of 30 degrees and the sides B and C encloses an angle of 90 degrees. If the acute angle between the diagonals is x degree, what is the value of x? So now first of all we have to construct the diagram as this is 6 2 root 3, this is A 4 root 3, this is B is equal to 9, and the point B has the coordinates 9 0, and this is C 9 and root 3. So now we can write here A, we have 0 0, the B as 90, C as 9 and square root of 3, and the value D we have 6 and 2 root 3. By using the concept of trigonometry, this is like 4 root 3 here A, and this is 30 degree. So we have the sine theta for P and H. So P is equal to, like if we draw a perpendicular partially, you can see the value of this dq is equal to, like sine theta is equal to dq by AD. This is like dq by AD 4 root 3. So this is 4 root 3 sine theta, and theta is 30 degree. So 4 root 3 sine 30 degree, and also for cos theta is equal to AQ by 4 root 3. So AQ is equal to 4 root 3 cos theta and 4 root 3 cos 30 degrees. So this is the value of abscissa and ordinate by simplifying 4 root 3 cos 30 degree and 4 root 3 sine 30 degrees. Now finally we have the coordinates of A, B, C and D. Now here we have to find the M for AC, and this is equal to, like root 3 by 9. This is slope for the AC. Root 3 by 9 is equal to 1 by 3 root 3, and now the slope for BD is equal to 0 minus 2 root 3 by 9 minus 6. This is equal to minus 2 by root 3. So the slope is negative, and now we have the value tan x is equal to, the two slopes are given, so the first slope minus second slope by 1 plus first slope into second slope. So this is equal to 1 by 3 root 3 plus 2 by root 3 by 1 minus 1 by 3 root 3 into 2 by root 3, and this is equal to 1 plus 6 by 3 root 3 and divide by 9 minus 2 by 9 in mod, and this is equal to square root of 3, and here we have tan x is equal to square root of 3. So we can write the value of x is equal to 60 degrees. So we got the value x is equal to 60 degrees. So in degrees we have the value 60 for the angle x. Now in the problem number 14, we have a function f is defined on the set of integers such that for any two integers m and n, f of mn plus 1 is equal to fm into fn minus m plus 2 holds, and f0 is equal to 1. Determine the largest positive integer n such that summation of k is equal to 1 to n, function of k is less than 100. Now we have the function of mn plus 1 is equal to function of m into function of n minus function of n minus m plus 2, and this is for we have f of 0 is equal to 1. If we use the value like the function of 1, and this will be like function of 0 into function of 0 minus function of 0 plus 2, and this will imply function of 1 is equal to 2. Basically here we are using m and n is equal to 0, and now let we have n is equal to 0, then we have function of 1 is equal to function of m into function of 0 minus function of 0 minus m plus 2, and this will imply function of m is equal to m plus 1, and function of mn plus 1 is equal to mn plus 2, and now function of m into function of n minus function of n minus m plus 2 is equal to m plus 1 into n plus 1 minus n minus 1 minus m and plus 2. Now we have the simplification for this, as mn plus m, so plus m minus m will be cancel out, then n and minus n will be cancel out, so we have mn plus 1 will be cancel out and 2 remains here, so mn plus 2 is the value. Now summation of k equals 1 up to n, function of k is equal to summation of k equals 1 up to n k plus 1 is equal to, we have like n plus 1 into n plus 2 divided by 2 minus 1 less than 100, and here we can write the value n squared plus 3n is less than 200, and this is for n is equal to 13 and n is equal to 12. So now for n is equal to 13 we have n square plus 3n is equal to 169 plus 39, and for n is equal to 12 we have 12 into 15, and this is equal to 180, which is less than 200, and this value is greater than 200. So now here we can use the value n as 12 for the required solution. Now we have the problem number 15. In this problem, there are 6 coupons numbered 1 to 6 envelopes, also numbered 1 to 6. The first 2 coupons are placed together in any one envelope. Similarly, the third and the fourth are placed together in a different envelope, and the last 2 are placed together in yet another different envelope. How many ways can this be done if no coupon is placed in the envelope having the same number as the coupon? So now in this case at first to the de-arrangement of 2 coupons can go in 4 of the envelopes. So we have to write the de-arrangement of 2 coupons goes into any 4 envelopes. I am considered E as envelope, and consider the first and second coupon. Consider first and second coupons goes into third envelope, and the total number of ways will be 4. Now we have f of x minus 4 times g of x is equal to k into x plus 2 into x minus 3, and this is for x is equal to 7, 12 plus 24, and this is equal to k into 7 plus 2 into 7 minus 3. So now we have, this is 7 plus 2 9, 7 minus 3 is equal to 4, so this is 36k. Now we have to use the value of k equals 1, and this will imply f5 minus 4 into g of 5 is equal to 5 plus 2 into 5 minus 3, and now f of 5 is equal to 7 into 2 plus 4 into 2 is equal to 22. So this is the final value of f5 is equal to 22. Now the problem number 17, here we have in this problem MTAI is a parallelogram of area 40 by 41, and such that MI is equal to 1 by MT if D is the least possible length of the diagonal MA, and D square is equal to A by B, then A and B are positive integers with the greatest common divisor is 1, and we have to find the modulus of the difference of A and B. So here we have first of all the parallelogram in the form I this is diagonal, y this is x, this is 1 by x, and this is also 1 by x. Now we have the area of parallelogram MTAI is equal to 40 by 11 as given in the problem. Now D is equal to MA, and 1 by x plus x is greater than MA, and MA is less than 2. Now we have the area of parallelogram MATI is also as in the form 2 into 1 by 2 into x into 1 by x sine theta, and here we can write the value of sine theta is equal to 40 by 41, because this will be cancelled out, 2 and 2 will be cancelled out, and sine theta is equal to the area of MATI, that is equal to 40 by 11. So sine theta is equal to 40 by 11, and same we can find the value of cos theta is equal to a square root of 1 minus sine square theta, and this is equal to a square root of 1 minus 40 by 41 whole square, and this is equal to 9 by 41. So now we have the values of sine theta and cos theta. So here we can write x square plus 1 by x square minus y square is equal to 9 by 41 into 2, and here the value of y square is equal to x square plus 1 by x square minus of 9 by 41 into 2, 9 into 18 by 41, and here we can write the value y square is greater than equal to 2 minus 18 by 41, and here the y square will be minimum on 2 minus 18 by 41, because we have the minimum value of y square is equal to 2 minus 18 by 41. So we have y square is equal to 64 by 41, and the difference of a and b will be 64 minus 41. This is already positive, so the solution will be 23. Now in problem number 18 we have let n be the number of 9-digit integers that can be obtained by permuting the digits of 22, 333, 4 times 4, and which have at least one 3 to the right of the rightmost occurrence of 4. What is the remainder when n is divided by 100? Now the ways to arrange 3 3s and 4 4s, where the rightmost among them is 3. So in this case, first of all we have to find the total number of ways, to arrange 3 and 4s, where the rightmost occurrence of 3 and 4s. So first of all we have to choose the rightmost among 3 and thereafter for 4. So for 3 we have the total 6 factorial by factorial 2 and factorial 4. This is 6 into 5 by 2. This is 15. And the ways to choose the position of 2 means 2 as a numbers and 9. So in this case the total is 9c2 is equal to 9 into 8 by 2, this is 36. So the total ways are 36 and 15 because together, so we have to multiply because the ways are using here together. So 36 into 15 and this is equal to 540, and the last two digits are 40. So we can see the number when divided by 100 will give the remainder 40, and we can write this as 540 is congruent to 40 mod 100. So here this is the final result for 40. Now this is the problem number 19. In this problem we have a triangle ABC, and in this triangle we have the angle B is equal to 90 degree, means this is right angle, and AB is equal to 1 and BC is equal to 2. On the side BC there are 2 points D and E. First of all we have to make a diagram. So for the construction we are first of all forming a triangle. This is a right angle triangle and the angle B is 90 degree. So this is angle B, this is A, this is C, and now we have to construct a circle taking radius AB. So this will be like this, and now this is this is D, this is E, this is F, and this is G. This is point H, and this is a square. So we are marking the length as A units, and we are dropping a perpendicular from H to the radius AB, and this is the foot of perpendicular I, and this length is equal to 1 minus 3a by 2. This is 2 minus 3a, and this is 2a. Here we have to take this point B on origin. So this is like having coordinates 0 and 0. So here B we have 0 and 0, A is equal to 0 1, G having coordinates 2 minus 3a and a, and ag is equal to 1. So this will imply 2 minus 3a whole square plus 1 minus a whole square is equal to 1, and this is 10. Now we have the problem number 20. In this problem, let f be the function defined by fn is equal to remainder when n to the power n is divisible by 7. For all positive integer n, find the smallest positive integer t such that function of n plus t is equal to function of n for all positive integers n. Now in this problem, first of all we have to use the Fermat-Last theorem. So here we have n to the power 7 is equal to n mod 7. This is what we are using, Fermat's little theorem for divisibility. So the power is prime, so this is valid for this, and now here we are consider here r is equal to remainder when n is divided by 7. Now in this case we have to arrange the values for the quotient and remainder. Now considering the quotient q is equal to 1 plus remainder when n minus 1 is divided by 6. This will imply n to the power n is equal to r to the power q mod 7, and now we have the value r as 1, 2, 3, 4, 5, 6 for q. So in this case we have the following results. For 1 we have 0, 1, 2, 3, 4, 5 and 6, and the corresponding values are 0, 1, 2, 3, 4, 5 and 6. The second, for 2 we have 0, 1, 4, 2, 2, 4, 1. For 3 we have 0, 1, 1, 6, 1, 6, 6. For 4 we have 0, 1, 2, 4, 4, 2 and 1. For 5 we have 0, 1, 4, 5, 2, 3, 6. For the value 6 we have 0, 1, 1, 1, 1, 1 and 1. Now for the all distinct and unique values of r, we have for the remainder, for r mod 7 and also q mod 6, for the following two cases there exists a unique n mod 7 into 6, 42. So here we have function of n plus 42 is equal to function of n, and we have the result as 42. Now in the problem number 21 we have, for some real numbers m, n and a positive integer a, the list a plus 1 n square m square a n plus 1 whole square consists of 3 consecutive integers written in increasing order. What is the largest possible value of m square? So now we have a plus 1 n square m square and a into n plus 1 whole square are consecutive integers in increasing order, and we have an square plus 2 times an plus a minus an square minus n square is equal to 2, and this will imply n square minus 2an minus a plus 2 is equal to 0, and now we have n minus a whole square is equal to a square plus a minus 2 is equal to a minus 2 into a plus 1, and we have n is equal to a plus minus a square root of a square plus a minus 2. Now here we have a plus 1 into n square is equal to a plus 1 into 2a square plus a minus 2 plus minus 2a square root of a square plus a minus 2, and this is for integers. And also we have a square plus a minus 2 is equal to k square, and this is for k belongs to integer. And now we have a plus 1 by 2 whole square minus k square is equal to 9 by 4, and here 2a plus 1 whole square minus 2k square is equal to 9, and this will imply the value k is equal to 2 and a is equal to 2, and this will imply the value of n is equal to 2 plus minus 2, this is 4 and 0. Now let we have first if n is equal to 4. When n is equal to 4, this will imply a plus 1 into n square is equal to 48, and this will imply a into n plus 1 whole square is equal to 50, and here this will imply m square is equal to 49. Also for k is equal to 0 and a is equal to 1, we have n is equal to 1 and a plus 1 into n square is equal to 2, and this will imply the value a into n plus 1 whole square is equal to 4, and here this is m square is equal to 3. Now if we use the value of here n is equal to 0, we have a plus 1 into n square is equal to 0, and this will imply a into n plus 1 whole square is equal to 2, and this will imply m square is equal to 1, and m square maximum is equal to 49. So finally we have the result is 49 here. Now the problem number 22, here we have there are m blue marbles and n red marbles on the table, and Arman and Babita play a game by taking turns. In each turn, the player has to pick a marble of the color of his/her choice. Arman starts first, and the player who picks the last red marbles wins. For how many choices of m and n with the value of m is greater than equal to 1 and n is less than equal to 11 can Arman force a win? Now in this case, the here there are m blue marbles and n red marbles on a table. So for how many choices of m and n with m is greater than equal to 1, n is less than equal to 11 can Arman forces a win? So starting at mn, if we start at mn, we can move to m minus 1 n or m n minus 1. For n is equal to 1, Arman winning case in all the condition. So when Arman wins in all the condition, he can just pick red by 11 cases. As m is greater than equal to 1 and less than equal to 11. And for n is greater than 1 and odd m, Arman can force opponent to pick from even pile of red marbles. So after no blue, ones are left. So we have to note here that Arman can force opponent to pick from red, and after no blue, ones are left. And here we have the cases for n is equal to 2, 4, 6, 8 and 10 all are even, and m is equal to 1, 3, 5, 7, 9, 11 for the odd choose. So here total 30 cases we have, and for the odd n is greater than 1, and when m is even, then we have taking the red marble, first make this an even number, red marble for the opponent. So here we have to choose the fourth win for Arman. So we have to write that Arman force his opponent with can guarantee a win if the number of blue marble m is even. So n is equal to here 3, 5, 7, 9, 11, and m is equal to 2, 4, 6, 8 and 10. So total 25 cases are here. So now if we see the 25 cases here, 30 cases here and 11 cases here, so total 25 plus 30 plus 11 is equal to 66 cases. So total number of cases will be 66. Now in problem number 23, we have a rectangle ABCD, and let M and N be points lying on the sides AB and BC respectively. Assume that MC is equal to CD and MD is equal to MN, and that points CD, MN lie on a circle. If AB by BC whole square is equal to M by N, where M and N are positive integers with the greatest common divisor Mn equals 1, what is the value of AB by BC whole square is equal to M by N, where M and N are positive integers with the greatest common divisor mn equals 1. What is the value of m plus n? Now in this case, first of all we have to form a rectangle and a circle. So this is a circle and this is a rectangle. A, B, C and D. This is point M and we are forming a triangle here. This is the point of intersection of the sides of rectangle and circle N, and here M meeting with N here, and we have to consider the value here, like this is the value alpha, and this is the angle 90 minus theta if we are considering this value theta, and now this is 90 degree minus theta, and this is also alpha, and this is angle theta. And this is like the value of AB and BC. AB and BC we have in terms of x root 2 cos 45 degrees by 2 and x cos 45 degrees by 2. So now we have the value of AB by BC is equal to x root 2 cos 45 degrees by 2 by x cos 45 degrees by 2, and this is equal to a square root of 2, and AB by BC whole square is equal to 2 by 1. This will imply 3. So we have the value of AB by BC whole square is equal to 3, and now this is the numerator is 2 and denominator is 1, so 2 plus 1 is equal to 3, as this is m, this is n, so m plus n is equal to 2 plus 1, this is equal to 3. So finally we have the value 3 here. Now we have the problem number 24. In this problem we have px is equal to x to the power 2025 and qx is equal to given. This is 4th degree polynomial. Let Rx be the polynomial remainder when the polynomial px is divided by the polynomial qx. Find R3. Now we have px is equal to x to the power 2025 and qx is equal to x to the power 4 plus x to the power 3 plus 2x squared plus x plus 1. This is equal to x squared plus x plus 1 into x squared plus 1. Now px is equal to qx into qx, and plus Rx. This is dividend, this is divisor, this is quotient, and this is remainder. So now we have px is equal to qx into qx plus Rx, as P of W is equal to R of W is equal to 1, and now P of W square is equal to R of W square is equal to 1. P of I is equal to R of I is equal to I, and P of minus I is equal to R of minus I is equal to minus I, and here this will imply Rx is equal to x square plus 1 into Ax plus B plus x square plus x plus 1 into Cx plus T. Now we have to put the values, then we find 1 plus W square into AW plus B is equal to 1, and this will imply minus AW square minus BW is equal to 1, and here this is A is equal to B is the case. Now I into Ci plus D is equal to I, and this will imply I into D minus C is equal to I, so D is equal to 1 and C is equal to 0. Now we have Rx is equal to x square plus 1 into x plus 1 plus x square plus x plus 1 and into 1, and this is equal to x cube plus 2x square plus 2x plus 2. And now if we put the value of x3, because we have to find r of 3, so if we put the value 3 here, we got 3 cube plus 2 into 3 square 9 plus 2 into 3 plus 2, this is equal to 53. So we have the value of r of 3 is equal to 53. Now the problem number 25 we have. In this problem, this is for how many numbers n in the set 1, 2, 3 up to 37 can be split the 2n numbers 1, 2 up to 2n into n pairs, and I is greater than equal to 1 less than equal to n, such that the product of ai plus bi from I is equal to 1 to n is a square. Now here we have to use the two cases. The first is for even and second is for odd. So now if we use the case A for n even numbers, we have 1, 2n, 2 and 2n minus 1, 3 and 2n minus 2, n and n plus 1. This is for the product of 1 to n, ai plus bi is equal to 2n plus 1 to the power n, and this is basically perfect square. Now here we have I is equal to 1 and square of n is equal to 2, 4, 6, and for 36 the total 18 solutions we have. And now for the second case, when we use n odd numbers, then in this case n is equal to 1. This is the pair like 1 and 2, and this is not perfect square. So if we use the second odd number n3, this is 1, 5, 2, 4, 3, 6, and this is basically like we have given the product for I is equal to 1 to 3 for the sum of ai plus bi. This is equal to 6 into 6 into 9 is equal to 324 is equal to 18 square. And now the square of n is equal to 3 is a solution. This is for n is greater than and equal to 3. We can include the value 3 also. So we can pair up to two terms to get the sum 9 and all other pair to get equal sum in two pairs. So we have n is equal to 7. So this will give 1, 2, 3, 4 up to 14, and 3, 6, then 1, 14, like 2, 13, like 4, 12, and also 5 and 11, then 7, 10, then 8, 9. So the solution exists for all except now this is problem number 26. Consider a sequence of real numbers of finite length, and consecutive 4 terms. Average of this sequence are strictly increasing, but consecutive 7 terms averages are strictly decreasing. What is the maximum possible length of such a sequence? So now, to solve this, first of all we have to see that if we use the sequences as t1 plus t I plus 1 plus t I plus 2 plus t I plus 3 less than t I plus 2 plus t I plus 3 plus t I plus 4, and this will imply the t I plus 4, and this is greater than t I for all I. Similarly, we have for t I plus 7 is less than t I for all I, and for n is equal to 11 we have t1 less than t5 less than t9, and also t2 less than t6 less than t10. Also we have t3 less than t7 less than t11. This is for t1 greater than t8. This is for t2 greater than t9, and this is for t3 is greater than t10. Now the fourth case is t4 less than t8 and t5 less than t9. So this is the case for t4 is greater than t11, and the last is t6 is less than t10, and also t7 is less than t11. So now if we combine all the cases, then t11 is greater than t7 is greater than t3 is greater than t10 is greater than t6 greater than t2 greater than t9 is greater than t5 is greater than t1 greater than t8 greater than t4 and greater than t11. So now there is a contradiction here, like if the sequence for n is equal to 11 is not possible, so we can write n is greater than equal to 11 is not possible, and for n is equal to 10, here t1 is less than t5 is less than t9, and also t2 is less than t6 is less than t10, and now we can write t3 is less than t7, t4 less than t8, and t5 is less than t9, and t6 less than t10, and also we have t7 is greater than t3 is greater than t10 is greater than t6 is greater than t2 is greater than t9 is greater than t5 is greater than t1 is greater than t8 is greater than t4. So the sequence for n is equal to 10 is the largest possible sequence. We can see here 1 2 3 4 5 6 7 8 9 10, and this is 1 2 3 4 5 6 7 8 9 10 11 and 12. So we have n is equal to 10 is the largest possible sequence. Total we have 1 2 3 4 5 6 7 8 9 10 11 12, and also this is the contradiction. So we have the largest sequence for n is equal to 10. Now the problem number 27. In this problem, find the number of ordered triple ABC of positive integers such that ABC is greater than equal to 1 and less than equal to 50. We satisfy the relation LCM of AC plus LCM of BC by A plus B is equal to 26C by 27. Here LCM is the lowest common multiple of the given numbers. So now first of all we have to see the GCD of AC is equal to G1 and GCD of BC is equal to G2, and LCM of AC is equal to L1 and LCM of BC is equal to L2. So hence we have L1 G1 is equal to AC and L2 G2 is equal to BC, and now let we have A is equal to G1x and B is equal to G2y, where GCD of xy is equal to 1. We have the value of LCM of AC plus LCM of BC by A plus B is equal to AC by G1 plus BC by G2, BC by G2, and this is divided by A plus B, and this is equal to G1 XC by G1 plus G2 YC by G2 divided by A plus B, and this is equal to 2BC by 27. Now this will imply 27x plus 27y is equal to 26 G1x plus 26 G2y, and this is x into 27 minus 26 G1 plus y into 27 minus 26 G2 less than 0, and this is for x into 27 minus 26 G1 plus y into 27 minus 26 G2 is equal to 0, and now this is if 27 minus 26 G1 is greater than 0, then we have 27 minus 26 G2 is less than 0, and this will imply 27 is greater than 26 G1, and also this is 27 is less than 26 G2. So we have G1 is greater than equal to 1 and G1 is equal to 1, and here AC is equal to 1, and now we have A is equal to X, B is equal to G2Y, then we have like A is equal to X is equal to Y, this is 26 G2 minus 27, and this is given that A is less than equal to 50 in the problem. So we have 26 G2 minus 27 is less than equal to 50, and now we have G2 is equal to and less than equal to 77 by 26. Now we can now have the value of G2 is equal to 1 and 2, because the G2 is less than equal to this value will only contain the value 1 and 2, because we cannot take 0. So you can see this is the value 77 by 26 is less than 3, slightly less than 3, and also for the value less than 3 we have 1 and 2 are the only intakes. So we can use G2 1 2, and if we have G1 is equal to 1, this means G2 is equal to 2, and now we have G1 is equal to 1 and G2 is equal to 2. So the greatest common divisor GCD of AC is equal to 1 and GCD of BC is equal to 2. So A is equal to 25Y is less than equal to 50, and C is even, and also if Y is equal to 1, it gives A is equal to 25, A is equal to 25, and A is equal to 25 and B is equal to 2, and the GCD of 25 and C is 1, means both are the co-primes. So total possible values of C, so we can write the total possible values of C in this case will be 20, and after revising A and B we'll get 20 more cases. So we have 20 into 2 is equal to 40. So we have total 40 cases are here. In problem number 28, we have to assume a is a positive integer with not a perfect square. Let xy be non-negative integers such that square root of x minus square root of x plus a is equal to square root of a minus y. What is the largest possible values of a such that a is less than 100? So now we have here a square root of x minus a square root of x plus a is equal to a square root of a minus y, and here xy belongs to whole numbers and a belongs to integer, and this is not a perfect square. So now by squaring both the side, we are squaring both the sides. Then we have x minus a square root of x plus a is equal to a plus y square minus 2y square root of a. And now the case a, we take y not equal to 0, then 2y square root of a is equal to if y not equal to 0, this will be irrational number, and by comparison, depends upon a, and now if we compare, then x is equal to a plus y square as equation a, then x plus a is equal to 4y square a, and this is equation b. By solving both a and b, we get the result as the value of a is equal to y square by 4y square minus 2, and this is equal to, this is 1 by 4 into 1 plus 2 by 4y square minus 2. And here y is the whole number and a is equal to 0, we are getting, which is not positive integer. So the case 2 here, if we have the case b, if y is equal to 0, we have x minus a square root of x plus a is equal to a, and x minus a is equal to a square root of x plus a, and here this will imply x square minus 2ax plus a square is equal to x plus a. Now we have x square minus 2ax plus a square is equal to x plus a, and if we use x square minus 2a plus 1 into x plus a square minus a as quadratic in x, because we have x belongs to integer, then the discriminant is a perfect square, because we have b square minus 4ac, like t is equal to 2a plus 1 minus 2a plus 1 whole square, b square minus 4 into a square minus a, this is 4a square plus 1 plus 4a minus 4a square, this is minus 4a square and plus 4a, this is like this will be cancelled out, and 4a plus 4a, this is 8a plus 1, this is the discriminant. So we have the value of this 8a plus 1 must be like if we use k, then for the perfect square this must be equal to k square, and if we see here, if we take a is equal to 91, then this will satisfy the condition, because we cannot take a is equal to 1 here. So here a is equal to 91 is the condition, as 91 into 8 plus 1, 729, this is the perfect square, and now we can write the largest possible value of a is 19. So 91. So 91 is the largest possible value of a. Now in the problem number 29, we have a regular polygon with n greater than or equal to 5 vertices is said to be colorful if it is possible to color the vertices using at most 6 colors, such that each vertex is colored with exactly one color, and such that any 5 consecutive vertices have different colors. Find the largest number n for which a regular polygon with n vertices is not colorful. So now let the colors be A, B, C, D, E and F are colors, and the sequence A, B, C, D, E be called the first sequence. This is the S1 first sequence, and the sequence A, B, C, D, E, F, this is called the largest sequence S. If we have n is greater than 0 is the number which represent in the form like 5i plus 6j for different values of I and j greater than or equal to 0, then n satisfies the condition of the problem. We may place I consecutive f sequences, consecutive S1 sequences. So this will follow the Z consecutive sequences, and this will follow the final S sequence. Now if we use the values for j is equal to 0, 1, 2, 3 or 4, like j is equal to 0, 1, 2, 3, 4, we find that may equal any number of the form 5i plus 5i plus 6 plus 5i plus 12 like 5 by plus 18, 5 by plus 24. So this will give the numbers as 5y, then 5y plus 6, 5y plus 12, 5y plus 18, 5y plus 24, and the only greater than 4 not of this form are 7, 8, 9, 13, 14 and 9. So we can use there exists a number k such that n is greater than 6k and less than 6 times k plus 1. So by the pigeonhole principle, at least k plus 1 vertices of n-gon have the same color. So between any two of these vertices are at least 4 other, because any 5 consecutive vertices have different colors. So we have the at least 5k plus 5 vertices, and n is greater than equal to 5k plus 5. So this inequality fails for n is equal to 7, 8, 9, 13, 14 and 19. This fails on. So this is also a contradiction. So hence a coloring is possible for n is greater than equal to 5 except 7, 8, 9, 13, 14 and 19. So we cannot use these numbers. So the final answer we have 19. Now the problem number 30. In this problem, we have let S be a circle of radius 10 with center O. Suppose S1 and S2 are two circles which touch S internally and intersect each other at two distinct points A and B. If angle OAB is equal to 90 degrees, what is the sum of radii of the two circles S1 and S2? So in this problem, first of all we have to construct a diagram as we can this is the circle. This is the two inner circles, and this is the called x-axis, and this is y-axis. We have and this is the point of tangent of these two circles, and this is from here this is the point of intersection of these two inner circles. This is QT is the coordinates of O1, this is B 2Q comma 0, this is 0 comma minus P, this is point origin 0 comma 0, naming A, and so these are the following arrangements for the coordinates of the points. Now if we use the radii of the given two inner circles, like R1 is equal to a square root of q square plus t square, and this will imply R1 square is equal to q square plus t square. And now as distance from the point O1, we have to use this and this coordinates. So we have the distance formula as distance between O and O1, and the R1 is equal to 10 we have, so a square root of q square plus t plus q whole square plus a square root of q square plus t square is equal to 10. A square root of q square plus t square plus p square plus 2pt plus r is equal to 10. A square root of q square plus